we hear about the Tesla that takes the off-ramp suddenly and just, crashes into something. Those things where you want that autonomy to save your life are necessarily going to be these edge cases that they don't have any data for.
What I usually say to our customers is we are giving a time machine to them. Instead of that years-long data collection cycle, we can just shorten it down to hours.
Today, we're talking about the $124 billion problem that Balint Pasztor and his team at DiffuseDrive has solved in just 1 year since launching this Silicon Valley startup. With DiffuseDrive already deployed across defense, robotics, and industrial automation by governments and Fortune 500 clients, we'll explore how this former national sports champion is applying the same team-first approach to transform the future of AI training.
Our autonomous driving background prompted us to just look at the problem. All the simulations, all the real-world data collections, all these things were just taking you so far.
I didn't really realize how big this problem was.
It's an eye-opening problem, but if you do our job correctly, then it's going to go seamless. So no one notices it, right?
Right,
That's the beauty of it.
Let's talk about examples of why this synthetic data is so important. Welcome, Balint.
Thank you so much for having me here, Chris. Happy to be here.
Yeah, this is going to be an exciting conversation because I think as we get deeper into this, people are like, it's going to be an eye-opener to a lot of people about like, oh my gosh, I didn't really realize how big this problem was. And I'm excited to talk about that, right? But before we get to that, I did mention you've got this, wild background. Can you give me the origin story? Give me your how you got from where you started to DiffuseDrive.
Absolutely happy to. And it's so funny because it's an eye-opening problem, but if you do our job correctly, then it's going to go seamless. So no one notices it, right?
Right,
That's the beauty of it. The way that we started DiffuseDrive is that me and my co-founder used to work at Bosch and doing high-level autonomous driving, and that pretty much like prompted us to be exposed to the problem of not having enough data. And if you're talking about all these autonomous systems, a car is just a robot on four wheels. So that means similar to drones, they are also using a different set of machinery to navigate the world, but at the same time, these are also robots. So all in all, what my background and my co-founder's background in robotics, in autonomous driving, in data, essentially is allowing us to solve this now. Originally, our Bosch background, our autonomous driving background, prompted us to just look at the problem in the first place. And before I get into that, the solution that we are bringing today, it wasn't apparent when we were facing this problem. All the simulations, all the real-world data collections, all these things were just taking you so far. That means that pretty much like everything, every dollar, every euro, every whatever currency that you were pouring into it was just pretty much going into an endless funnel. That means that the data collections were long. That means that you have to pay a lot of people over time. You have to pay a lot of machinery to collect data. And more specifically for autonomous driving, it was the case that the highlight was that the spotlight was there. But for anything else that is not autonomous driving, it wasn't even the case that they were able to collect it. But then again, going back to our time, so we were facing data shortage. We were facing essentially the fact that we wanted to develop, the models were ready to be trained and developed, but the data wasn't available. And me and my co-founder both worked and ran this internal startup. I don't want to be secretive about it, but also it's not public information, so I cannot share everything about it. But then definitely it was one of those eye-opening cases. It's like, we want to go fast. We know the direction where we want to go, but we cannot because there is this huge limiting factor. And that's the same thing for Tesla. That's the same thing for Cruise or Waymo or these companies of the world. And of course, that's the same case for anything that is an autonomous system in defense, in civil applications, in manufacturing. So like pretty much anything that needs to see and understand the world needs three things essentially: the hardware that it runs on, of course the AI models, and of course you need the data for the AI models to perform really well. And at the end of the day, these three together make the performance high. If one of them is missing, then you can do so much.
I think it's worth noting, prior to the LLM revolution that's come about here, we always imagined that there was just so much data that we had been collecting and that we had that we would just be able to look at that data and create artificial intelligence systems from that kind of data, right? But then, like this LLM revolution hit, and it was amazing how fast we exhausted all the good data. And that is a big problem, right?
I think you were tapping in the right direction. The good data.
Yes.
When we're talking about data itself, of course, we have a bunch of sources where we can get even more data. And the problem there is that, of course, most of them are junk. And I don't want to use any heavier language, but pretty much like 99% of we have to just throw it into trash, if not more. Same case for autonomous driving, same case for any robotics. And of course, LLMs, right? Those are interesting AI models that you have to train with tremendous amount of data. But before the LLMs, and it's so funny because everyone was doing natural language processing. That was the precursor of the LLM.
Right.
LLMs, and like everyone with the mother wanted to do that. And we were losing people, autonomous driving, to NLP people or NLP companies, because that was the hot thing at that time, and not autonomous driving anymore. I remember at Bosch we were trying to hire a couple of people, and like pretty much we were competing in NLP. And it's so funny, like one is like a robotics application, the other one is language, as much as it's wonderful, but definitely not my place to say anything about it. But for sure, one of those cases where it's like those are the cool things, and you just have to compete with the cool.
Yeah. Kids want to go do the cool stuff.
Yeah.
So talk about though this. I mean, I call it a $124 billion problem, right? I mean, it's probably bigger than that. What happens when we don't have this data? I mean, I think we have some real world examples of where not having this data has really constrained what we can and cannot do.
Essentially, when you're not having the right data, for the underlying models, they are not going to perform well. So usually what people say for autonomous driving, it's been always around in 5 years, right? But that's been the case for the next 20 years. Same thing for autonomous planes, same thing for autonomous drones, same thing is for anything that needs to see and understand the world that actually is able to perform tasks in the real world. So not just vanity metrics where we are like, okay, but we can already do something. Yes, to an extent, we have enough data to do like low-level autonomy, low-level and value-add stuff. Same thing for humanoid robots. So anything, again, that needs to see and understand the world. And the problem here is that if you don't have the right data, you're going to hurt someone. So in safety-critical applications, wherever humans are involved, of course, you don't want to hurt them. And for some other tasks where it is mission critical, let it be defense, then of course it's also another layer of complexity where you need to have the data. If you don't have it, then someone is going to get hurt, and hopefully it's not the wrong person that gets hurt. There was a unfortunately gruesome example of what Cruise has happened to overcome. Not as much, unfortunately. In San Francisco, a couple of years ago, they had this problem where someone fell under the car, and of course, falling under the car is not an example that happens really frequently. These are called edge cases or long tail cases, depending on how we are defining them. And I think in the introduction you mentioned that the edge cases are the ones that are making and breaking the algorithms, and more specifically, those are the ones that we need to find, we need to capture, we need to have in our data sets, or in other words, you have to show them to the machines to understand them, to extrapolate from them, so that we can have real autonomous systems that actually understand the world. One thing that we a lot of time forget is that the machines don't have intuition. That means that they cannot really extrapolate from the data that they haven't seen yet, or from the data that they have seen into something that they haven't seen yet. So we have to be able to show examples to them, examples of how the world looks like, how the world behaves like, and what we are expecting from them. And those are pretty much the data points that we are generating at DiffuseDrive. But before going into that is the one of the most important things, is that this problem that we are solving is not just not just making it like a little bit better. We are still at the point where autonomous driving or autonomous systems. I usually bring up autonomous driving because this is something that we always
We can relate
always
to.
see.
Yeah.
Exactly, because everyone has a car or everyone has sat on a car already in their life, and we can see that, like, especially in San Francisco. Right now, I'm in San Francisco. You can already see the autonomous driving companies just roaming the city, and it's becoming like second nature to people. But at the same time, that's gonna be one of the first applications that's gonna be actually widespread in the world. So getting back to that point, it's not only that we are just making it like a little bit better. We are making sure that it can be deployed everywhere. That's the same thing for drones. That's the same thing for household appliances. But funnily enough, most of the applications are gonna be in places where you're never gonna see them, in manufacturing, in construction, in agriculture, so that everyone has a fair shot of accessing all those products that they are producing.
Let's talk about like examples of like what that looks like, because I think it's hard to like really wrap your head around why this kind of synthetic data is so important until you understand like what's going on there. Because like we have autonomous vehicles, right? And they're built in San Francisco, or they're trained in San Francisco on San Francisco conditions and things like that. We have a lot of data of people just driving, right? But the thing that makes everybody uncomfortable about these autonomous vehicles is sort of those edge cases, right? We hear about the Tesla that, like takes the off ramp suddenly and just, crashes into something. Those things where you want that autonomy to save your life are necessarily going to be these edge cases that they don't have any data for, because it would be unethical to crash, have, 50,000 people crash in their cars just to train, the car on different scenarios that are very complex edge cases. It would be unethical, say, to operate on a lot of people and look at all the different internal organs, how they present themselves in the different people, and make all those surgical mistakes while trying to do this. So like there's going to be cases like weather or climate, or you talk about battlefield kind of applications. I mean, like, what does this thing look like when it's blown up, right? You can't just go and blow up everything and then, like use that for training data, right? So like, I think when you put that in your head, that's how big this problem is. Like, it's like this technology can't really advance unless you have the kind of data that you're talking about. This episode of IT Visionaries is brought to you by Meter, the company building better networks. Businesses today are frustrated with outdated providers, rigid pricing, and fragmented tools. Meter changes that with a single integrated solution that covers everything: wired, wireless, and even cellular networking. They design the hardware, write the firmware, build the software, and manage it all so your team doesn't have to. That means you get fast, secure, and scalable connectivity without the complexity of juggling multiple providers. Thanks to Meter for sponsoring. Go to meter.com/ITV to book a demo now. That's meter.com/ITV.
And funny enough, as you were mentioning, like why synthetic data itself is really relevant is because in an ideal world, we would have infinite amount of resources, money, infinite amount of time, which would be a wonderful world. We don't have it, unfortunately. We are living in an engineering world, or that's what I usually say to my friends. It's like, unfortunately, we have constraints. Most usually it's time and money.
Yeah.
And that's true for the companies as well that are developing it. So in this case, I usually bring this example, like really dumb it down. Chris, how would you describe a dog? How does a dog look like?
It's got 4 legs.
Okay.
It's got 2 flappy ears, and most likely it's got hair. Okay.
So would that fit only on dogs?
No, it wouldn't.
And that's pretty much the problem. Of course, I'm talking about rule-based and then machine learning-based. And of course, for machine learning-based, we are talking about, not pre-describing it, but of course, showing examples. But if I only show, let's say, 100 dogs for you, that only has dogs that are like healthy, am I gonna recognize the next one, which only has 3 legs, right? Because for some reason, it only has 3 legs. Or hairless, or like anything, right? So extrapolating from this is not easy. So taking this into more complex situations, let's take an easy example. We have already sat in a car, all of us, most probably, and we have already seen how an automatic emergency braking system works. Essentially, when it recognizes that something is close, it will stop or try to stop for you or try to help you stop. Now, for this, essentially, anything is an edge case that will trigger this system, right? So that means anything that is close to you and is on the road will trigger the system. Now, how many times have you seen this happen when you're driving? Probably you remember a couple of times, right? But compared to how many miles, hours, or like whatever that you define, like how much you have driven before, like just think about it. In the day, let's say you drive 2 hours, 1 hour to your work and 1 hour back, and then one thing happened. So that means 2 hours worth of data recording would yield you one if it actually happens. Most usually it doesn't even happen.
Right.
So that's the level of infrequency that we are talking about. And then of course we can go down to the long tail cases where you are like really infrequently encountering things. And the problem there is, of course, like the more that you are recording, it doesn't necessarily mean that you will get everything from the real world. That means that you need to supplement this with synthetically created data that looks like, breathes like, speaks like the real world. Unfortunately, the previous generations of the ways that people were doing synthetic data doesn't yield as good results as there was possibility for, right? There was something called simulation to real world gap. That meant that essentially everything that you trained with simulation data or synthetic data at the time didn't yield you a real world performance increase. It was the problem of not having like realistic imagery, realistic representation of the real world. Now, what we have figured out is, of course, taking a different technology, diffusion models in the core of the system, and bridging this gap, making it indistinguishable from real life. Pretty much like if you were to look at and if you go to our website, DiffuseDrive.com, of course, you can also see that. And there is one of the sections where we are showing real imagery and then generated imagery that look exactly like that. You wouldn't be able to distinguish. Couple of things that are making sure the camera characteristics are baked in. Then, of course, the situation, whatever that might be, let it be a satellite, I think there is a satellite in there. There is an automotive use case, and there is something else that I can't seem to remember now, but pretty much like within the realms of what we are solving. And then pretty much you cannot distinguish. What distinguishes the real world and the synthetic ones is that the scenes and the scenarios that we are regenerating, or rather creating for our customers, are different. So that means something that they haven't seen before. All those long tail cases or edge cases that are infrequently happen, we don't make them to record another 2 hours so that they find one of the things that might trigger the emergency braking, but we are generating all those cases that are triggering the emergency braking, or in other cases, the parking situations, or in other cases for drones, finding the friendly troops in battlefield actions, or for one of our customers, we are generating birds and drones because it's hard to distinguish them. For some, it's maritime applications. For some, it's quality assurance and quality control in manufacturing cases where we are generating faulty products. Most usually they don't have faulty products because the manufacturing is good, but then they have to find what is not good so that they can sort it out, right? And then that's
especially if the AI is there to identify when something goes wrong, and you don't have any examples of that. Yeah,
exactly. So all in all, that's pretty much like how graphic it could be. So think about it like what could go wrong in the applications. We are generating all those cases, or what could go right. But that most usually is the easier part.
Yeah.
What could go right?
So I got a couple questions for you here. So like, can we just back up for a second and talk about what a diffusion model is for people who don't understand what diffusion models are?
So essentially, if you were to have an imagery, let's say a picture of a dog, I'll take this and pretty much add noise to it in a couple of steps. I add noise a little bit so it becomes a little bit grainy. So this is step one. Then another level of noise. And then that's going to be step 2. Yada. We get to step, let's say 500, where it's completely noise. Those that were born before like 2000 have seen the list. old TVs with pretty much the static noise appearing on it. That's pretty much to the level where you're getting to. So these are called noising algorithms. And then on the reverse, these are called denoising algorithms. So what we are teaching the system, or what some of the other companies are also teaching these systems, is to be able to denoise pictures or fully noisy spaces so that it becomes something that we can understand. In this case, we can reverse noise it, and then it becomes a dog. And then basically from these white noises, we are generating imagery that satisfies the conditions. The conditions are most usually the prompts, so it will have a dog on it, and then we generate a lot of different dogs. It will satisfy the conditions, and of course, it's going to introduce diversity into the whole system, because the seed, the noisy picture or the noisy image in the first place, is different. All those companies that are using imagery production as well as a couple other modalities to create new things. So it's part of generative AI. And generative AI essentially is creating something from nothing, but something is the one that we are like constraining. And of course, then the nothing is being the white noise. And of course, the diffusion model is just one way of generative AI. Of course, the transformer models are the other big one, if not the bigger one. The language models most usually are using transformers. So one of the examples is general purpose transformer, or GPT. And of course, we are seeing like intersections of the two, like diffusion transformer models. So the future, especially about the generative AI space, is just wonderful. And I think we are yet to see another big boom just in the underlying architecture.
I want to go back to that, like the comment you meant about sort of like the novel situations, right? And you talk about manufacturing. It sounds like, could this be a way for a company that's going to bring a new factory or plant online, and it's going to use artificial intelligence, robotics to manufacture these products, but the product doesn't exist, the factory doesn't exist, but you still need to train the AI. Is this something that you could, take that and like build the training data to actually make that happen?
You are tapping in the right direction. So what I usually say to our customers is we are giving a time machine to them, and without being like too marketing-y.
Yeah.
The reason I'm most usually saying this is, instead of collecting data about the use case, about the product that they are trying to manufacture, and of course all the things that they might be able to see regarding like quality assurance issues, is that instead of that years long, like literal multiple years long data collection cycle, we can just shorten it down to hours. So in this case, it's not a time machine that goes back in time, but definitely shortens the time for you. And more specifically, our customers are using to expand data sets. Our customers are using it for building up data sets from the ground up. So absolutely, you are tapping in the right direction. Pretty much, if it already exists on paper, already have a couple imagery about it, we can already have them.
There's an interesting challenge in all of this, right? Because you have the capability with your system, I would imagine, to, generate like a cinematic, beautiful, image, 4K image of, that's, movie quality. But the cameras that are in use are nowhere near that quality, right? And I would imagine, like going back to the car example, if you coming from San Francisco, where it's generally warm, when it's not supposed to be warm, it's warm. When it's supposed to be warm, it's usually cold. But, like come to here in Chicago, where, we've got, it seems like 11 months of snow, and, like you've got snow on a camera, you got soot and grime and stuff like that. So, I mean, like, is that something you have to simulate, or like how does that all work?
Absolutely. I mean, that's pretty much intricacies of the real world are the deal killers, essentially. So if you were to generate something that is like completely perfect, and that's what simulations were doing in the first place, because they were trying to like, okay, see how I can do ray tracing. It's beautiful. It really behaves like the real world, but it is just too perfect. There is always this uncanny valley where you are like, it looks really good. It could be in the real world, but there is always this substance that you are like, I'm not sure. And then, of course, even the best ones are, you're like, but there is still a leap that we need to do. So essentially, there are a couple of things. Of course, we live in an engineering world, as I mentioned, and unfortunately, those cameras are sometimes crap. Sorry for the language, but like sometimes cheap, right?
Yeah.
And that means that the quality is not the highest because, of course, you have to go through procurement. You have a limited bill of materials. You have a limited budget.
And they're operating under difficult conditions too sometimes,
Of course,
right?
of course. And sometimes it's just that. And of course, external things like smudge on the camera, like adverse weather scenarios, everything pretty much like is against you. So if you were to train everything on perfect conditions, you would work flawlessly in perfect conditions. I don't know when was the last time that you have seen perfect conditions.
Yeah,
Not even in
get
California.
No.
So the sunshine tax doesn't cover that around here. So
no.
But essentially, the way that we are approaching it is, of course, if we were to do perfect, then that would be really not useful. We would just be recreating the same problem as what people had with the simulations. So what we are doing is essentially introducing the diversity, and the diversity essentially is on the imperfection side as well. So if you were to look at it, what we are producing, and please look at it on our website, you would see that there is always this like something small that it's like, it makes it real. That is the reflections on the road, of course, the correct angles, the correct shadows. And of course, if you are to look at it, there is no two place that we are reproducing necessarily that have all these small details in the same place. So there might be a different time of the day, different type of wind conditions, so that the grass doesn't look the same. The intricacies, the small details that make it different. I think that's one of the most important part.
And like it makes me think about another scenario too. I mean, like we talked about the manufacturing piece where maybe you do have a lot of imagery from the line, but you're upgrading the line and you're putting new cameras in. And like maybe you had black and white cameras before. I mean, is that any of that data good now that you've got color cameras and you've changed the system up? IT Visionaries is powered today by Meter because every great business relies on great networks. If you're a network engineer, you know how critical uptime, control, and visibility are. Too often, you're stuck troubleshooting issues across fragmented systems or locked into legacy solutions that don't scale. Meter reimagines networking from the ground up. Their full stack solution from ISP procurement to security, routing, wireless, and beyond gives you deep control and the performance you need. No more piecing together providers or worrying about bottlenecks. Just seamless, scalable connectivity built for today and tomorrow. Big thanks to Meter for sponsoring. Visit meter.com/ITV to book your demo now. That's meter.com/ITV.
So far, we were talking about the data itself, like the synthetic data production. But of course, figuring out like what data you need is another one. Like, of course, like I'm upgrading. Okay, but what can I use from the previous one? Or in other words, given the constraints of what you are designing your system for, or the operational design domain, what you're using it for, pretty much using that and using a couple of reasoning models and like our own proprietary system to look at the data, what's there, what's missing compared to an ideal case, and then suggesting, okay, but you are missing, if it's a manufacturing scenario, you are now missing the wide angle cameras. You are now missing the ones that the product that is being discolored. You cannot really reliably find those. And like all these different things are coming out of the first system, or in other words, we have 3 steps that we are doing the data layer, essentially for our customers. In the middle, of course, is the synthetic data. But the first step is that finding out, okay, what's missing, what actually is missing, so that if you are upgrading your line or just introducing a new product that you want to run on the same line, or pretty much all these variations that you could do. And besides, of course, improving the already existing system, we can help you understand what's there, what's missing, and of course, then give you all these suggestions. Create this, create that, create A, B, C, D. And then, of course, that is all for improving performance. So these 3 steps that we are doing, and I'm going to talk about the third one as well, but these are all for increasing performance in the AI systems that is being deployed in manufacturing, in drones, in cars, in construction vehicles.
There's an aspect to all of this that the newness doesn't show us yet. And that's that all these systems are going to be upgraded at some point. So they're going to be improved upon. And when you improve upon them, that may break all your training data. And the world changes. I mean, like from when I was a kid to now, the street signs have gone through many different iterations of things, for example. And what happens when there's like a new street sign? Do you take all the cars off the road and wait until you've got enough training data to feed those algorithms? I mean, like
Yes.
how is that all going to work?
And of course, the other thing is that you are always trying to expand what your capability is. So in the first place, we only had cars. We only had lane keep assist. Then we wanted to do a little bit more and a little bit more and a little bit more. So if we were to look back for probably for this time, like 20 years from now, we'd be laughing. It's like, oh, so your humanoid robot was able to do that, or your Roomba at home wasn't capable of making you breakfast in the morning. There's always going to be more data need because the capability, the operational design domain is going to increase. And of course, the other one is that even the underlying performance in the given operational design domain, without expanding that, it could be always improved. There's of course a cutoff point where you are like, okay, it already satisfies it. Let's see if just the base capability need to be improved, or we expand the capability set.
Well, I got to imagine, like I've heard people talking about model drift and things like that. I mean, I got to imagine you are going to play a big part in fixing those kinds of things.
And that's what we are trying to like highly avoid, model drift.
Yeah.
So we most usually don't recommend using the synthetic data for training another synthetic data provider, with the small caveat that we are also using our own data, as in like our system, to filter out the bad data. So it only matters if there is hallucination in there, in something that doesn't belong to the real world, or rather something that we need to filter out. So we are building our own system to filter out hallucinations and the artifacts in the systems. And once it becomes the same as the real world, then of course you can narrow it down. But for edge AI applications, or for anything that is deployed on the edge, that could be a car, a drone, even a camera, for that synthetic data plays a significant role.
Let's talk about that, because I think when we talk about like creating this data, this image data, we've all seen, the people with like 10 fingers per hand, or, like, I watched one presentation recently where all the images were auto-generated. Not a single person had the right amount of fingers on their hand. So we see, that happens a lot. And so we see a lot of hallucination in these models. Like, so how do you control against that? Like, that's got to be a big challenge.
Without going into many details, there are two ways to control them. Of course, what goes into these generation models and what comes out needs to be filtered. And of course, we are using a couple different methods to just control what goes into them. So controllability is a huge and important issue that we are hopefully solving, and especially that requires less oversight at the other end as well. So if you're controlling it well, whatever comes out of it is already significantly less and infected with hallucinations. And of course, when they come out, there's going to be hallucination, especially with this. Within our product, we are using different agents that we have built to do the quality assurance, the quality control for ourselves, discriminator layers, verifying agents, so that they are looking at the different parts of the imagery, or in other words, the features of the imagery, and then looking at the correlation between them, and looking at the correlation between performance and the imagery that we are generating, benchmarking them essentially. And that makes sure that whatever ends up at our customers is already usable. So if you were to use these diffusion models off the shelf, similar to if you were to use GPT off the shelf, well, you wouldn't have a good time. Let's just put it this way. You would be like, okay, I'm not going to use it ever again. But then again, when you're using products that are designed to give you the best result, then it becomes more interesting.
The more we dig into this, like there's a lot of the devil's in the details here in how this all works. Through the process of developing this system, you must have encountered some really interesting challenges that you had to overcome, and some really kind of non-obvious problems. Like, for example, like just figuring out how to make the lens, like similar to whatever, that probably was initially kind of a non-obvious sort of problem that you had to solve for. But like, what other kinds of, challenges like that did you encounter that you had to overcome?
The non-obvious thing is articulating what needs to be there.
Yeah.
So the first part of our product essentially is solving that, or rather helping our customers to articulate what they need. So instead of actually going to our customers, okay, here is the tool, use it however you want to use it. We are helping them to understand what's already present in the data set. So think about like what a data scientist would do, to go through the data, to filter it, to clean it, to have like a registry of what's in there. We are giving this to our customers without them having to employ multiple people just working on the data itself. And then we are giving them a way to understand it instead of employing these lot of people, spending a significant amount of time of their employment. We are giving them as a means to understand what's there, what's missing. And this wasn't obvious in the first place. There has been already many attempts about just having a unified language to describe the scenarios, scenario definition languages. These are the common words for that, but they don't work. That's a big problem. Is that even though it's unified, even though it's like somewhat common, it just doesn't work. And of course, like the more requirements we have from external validators, external government agencies and stuff like that, then it becomes messy. So what we are doing is pretty much using the ability of the reasoning models, the language models, to interpret human interpretable things. It could be documents, it could be requirements management, all these different things that humans are able to just understand. We are now pretty much like dumping it on them, and then dumping more and more information to our customers so that they understand what's present there and then what they need to generate, because that's the important part. What's going to move the needle for you?
So you're helping them understand what is in their data. You identify what's in their data, but that data may not be as good as it could be. I mean, would you...
Most usually it's not.
Most usually it's not. Would you be potentially replacing some of that data to give it more deliberate results?
And that's the third part. So thank you for bringing that up.
Well, good.
So the third part essentially is making sure that whatever comes out of our system is usable. And then, of course, like mixing it into the original data sets. And then looking at, okay, how do you want to train and how do you want to validate it? So splitting the already existing data, getting rid of the things that are repetitive. So you don't want to overfit to a certain type of scene and scenario. That's a really interesting problem, because if you only have, let's say, you only record things in California, right? So you will have a lot of sunshine, and then you would be performing somewhat well in sunshine. And then what happens in Chicago? And the same thing that you brought up a minute ago, that's pretty much is the same problem and like you can expand that into other domains as well.
Yeah.
But you're not going to be able to do that because you overfitted. Even though if you have, let's say, a little bit of intermediary, you'd still need to have like significantly more or balancing the unbalanced data set so that you can actually work well and not just overfit to, well, California is beautiful, but this is not the only place in the world.
Well, I think that's kind of a non-obvious problem right there, because like just I have more data, so I'm just my model's gonna lean more heavily towards this rather than perhaps the scenario that I need it to apply to. Yeah, I mean that's interesting. And then like you can, I guess the two ways to deal with it is like either pare back some of that data or just add a ton of its other data.
Exactly. And the other thing is you don't usually need it. So even if you have millions of data points, the other day I was visiting one of our potential customers, and they were saying that they have over 1 billion data points and they are only using 1 million or so for training. And that's reasonable, because even if you had like all of them, let's say theoretically all of them are useful, you would still need to dial it down because you are dealing with computation, training costs, and like all of these different things. And ideally, you would want to have like the best possible outcome from the given resources. And that's what we are helping our customers. So the same spread that we established in the first place, that we started filling with the second step. The third step essentially is helping us. Okay, so based on the spread, this is where the training and the validation data should go to. Ideally, you can actually measure what you trained for.
That's interesting. I mean, would you say that like when there's too much data in the system, that it could lead to incorrect interpretations of some of that data that leads to really unexpected emergent behaviors?
Yes and no. So if you have diverse enough data, and of course, just grabbing this like diverse enough, like what's diversity? So you have the coverage for all the possible scenarios that you could have. Ideally, that would be the case for everyone, right? But it's not the case. Unfortunately, the amount doesn't necessarily correlate with performance. Actually, usually it doesn't correlate with performance.
Yeah.
And the more that you have of the same thing, you're not going to learn more. If I were to show you, just getting back to the dog example, if I were to show you 1,000 dog, you would have a really good understanding what's a dog. 1,000,000 dog, you would have a really good understanding of dogs. But like anything from there, it's not going to change your understanding of dog. It's going to be a little bit more granular. But then again, what if it comes to cats?
Yeah, and if you only have 1,000 images of cats and 1,000,000 images of dogs, it's going to go, well, this is probably a dog, actually, right?
Yeah, and that's going to be a problem because it will be like the confidence level for dog is a little bit higher, so I'm going to categorize it as a dog. And of course, it's an easy example. You could take a right turn. You could take someone is cutting you off in the traffic. You are flying a helicopter and want to automatically land. You are in the battlefield and you have this ground autonomy, a small drone that you are trying to control. So all of these things are essentially the same thing. It's just the dog example is the simplified version.
You have this sort of feedback mechanism so that you can kind of evaluate the performance of your data. And I got to imagine it's really interesting to see how that all plays out when you start, like saying this data is better than this data. We've got a lot of data, but we don't need all this data. But what stays and what goes. And I got to imagine that can drastically improve your model's performance, Absolutely. Right?
I mean, that's pretty much like how we are seeing is that ideally we would have the best performing data for the best performance. And the third part of the third leg, if you will, of our product is pretty much helping our customers to find the best split.
Yeah. Wow. That's, yeah. I mean, the more you dig into this stuff, the more it just starts to blow your mind.
Yeah, if you were to look at it from afar, we are helping our customers to get the best performance. And it takes understanding it, it takes getting it, and it takes splitting it or curating it rather.
Yeah.
And we are helping that. So combined, we are just giving a time machine that is quick enough.
Yeah. And it seems like that's a lot of what the problem is with, when we're using these tools today is we've got a lot of data, but we don't know how good the data is entirely. We've just kind of gone with quantity over quality. And I think and in anything in the world, editing is so important to getting a good result. This is amazing stuff. And I can see how our future will be limited without these kinds of technologies. Where do you see all this going? What's next for the industry? What's next for DiffuseDrive?
So ideally, where we are going with autonomous systems is that if we are doing our job well, and I'm considering ourselves as part of the solution, then we're going to have enough automation that our life becomes significantly better. That means we don't have to drive, we don't have to do mundane things, and I'm talking about commuting, not driving. I'm a motorcycle rider. I love doing that. I love smelling gas for that, but of course,
we will drive for pleasure, not for utility.
Exactly. That's the right way of saying it. But that's the same thing for manufacturing. It's going to get to a level when it's cheap enough. Or just agriculture, we have better food. Or construction, we have more affordable housing because it is affordable. At the same time, of course, it's replacing some of the mundane and dangerous jobs that people are doing. So this is where it's heading, of course. This is the utopic vision. Yeah. And in the immediate short term, I think what we are solving here and us with our customers is all of the things that we were talking about 10 years ago can actually manifest the manufacturing plants. The quality assurance, these safety applications, the safety relevant applications, and of course the defense applications, the mission critical features of everything that has been deployed over the last couple of years, and now they can actually be autonomous. And that's where we are heading. And what's DiffuseDrive is doing, we want to be the default data engine for the autonomous systems for physical AI. I think that's the word coined by, well, not coined, but really frequently repeated by Jensen Huang from NVIDIA. The physical AI part is the biggest frontier. So why I'm excited about solving this and why probably Roland and the whole team is excited about solving is that AI needs the last frontier to be conquered, which is the physical touch. And that's pretty much where we are heading to. I don't want to talk about AGI or ASI. It's more about like true artificial intelligence. And that's going to be something that actually is changing our lives. And of course, language models are like going to be really helpful in many other ways, but physically touching something and then affecting it will be the case for physical AI.
AI and what you're doing is helping us understand the past and how things have existed in the world. But the thing that's interesting about what you're doing is it helps us imagine the future a bit too. And so we can create our future and sort of manifest it by giving the AI the data it needs to create that future.
Exactly. And these AI systems are going to affect our lives one way or another. We might have the humanoid robots at one point at home. I'm like a little bit skeptical about the utility of some of them. But then again, like if you have a platform that is just cheap enough, then you can deploy them everywhere. And there are so many companies just in San Francisco. The other day I was meeting with the company doing right now teleoperation, and then eventually, of course, collecting a lot of data so that they can deploy it with the help of ours, of course. And then, of course, there are other like foundational model companies that are just going to be amazing, hopefully. Like that's where my hope is about different physical AI applications. So it's a really interesting time to be alive, especially building a company in the field. So wouldn't be wishing for any other time in the history. And then we're yet to see what the future brings for us.
Yeah, that's super exciting. A really interesting company, really, really interesting problem space that you've gotten yourself into to solve cool problems. And I'm excited to see where you go from here. Thanks so much for being on. I really appreciate it.
Thank you so much, Chris. And if you were to bring anything with yourself, it's DiffuseDrive is just solving data scarcity for physical AI. And that entails everything of physical AI being super fun. And most usually, sorry, just one more anecdote. Most usually our customers are the ones that are doing the interesting, the fun, the fancy stuff. And we are doing the boring, or rather the mundane things that underlies so that they can do their job better. For us, it's actually funny that I think it's really enjoyable, but for sure, it's not the fanciest. This is not the shiniest thing.
I think you're underestimating how cool what you're doing is. So,
well, then thank
I'll
you
leave
so
it
much.
at that. Thanks so much.
I appreciate it, Chris.